In this video, we're going to talk about integrating trig functions. So let's recall from Calculus 1 the following derivative formulas. So remember, the derivative of sine is cosine, the derivative of cosine is negative sine, the derivative of tangent is secant squared, right? The derivative of secant is secant times tangent, right? We have these derivative formulas from Calculus 1. So each of these derivative formulas also really gives us an integral formula, right? So the integral of cosine would be sine, or the integral of secant squared would be tangent, right? Plus c, of course. Okay, but the question is, how do we do integrals like these ones here? So that's what we're going to talk about in this video. How do we integrate like sine to the 6th power times cosine? Okay, or the integral of cosine squared, or the integral of secant, right? So notice that the derivative of secant is secant times tangent, but what's the integral of secant? Well, notice on the right-hand side, I don't see secant anywhere on the right-hand side here. Okay, so none of these formulas will give us the integral of secant here directly. So how do we find the integral of secant? Or same thing with tangent, integral of tangent, or integral of tangent squared, or integral of cosine of 5x times sine of 3x, right? The integral of tangent to the 5th times secant to the 4th. So all these are called trig integrals, right? Because they're just integrals that involve trig functions. And so in this video, we're going to talk about how would we do these. Okay, so let's begin. First of all, how would we integrate cotangent of x? Now again, notice on the right-hand side, there's nothing that's just cotangent of x. We have the derivative of cotangent is negative cosecant squared, but the integral of cotangent we can't find just based on this table. So how can we integrate cotangent? Well, we can write cotangent as cosine over sine. Remember, tangent is sine over cosine, but cotangent is the flip of that, cosine over sine. And it turns out we can just do a u substitution. We can let u be sine, and if we do, then the du will be cosine of x dx. So notice what we have is the integral of, well, the cosine x dx is the du, and the sine down here is the u. So this is just the integral of 1 over u du. And notice that the integral of 1 over u du, if you remember, is natural log of u, or natural log of the absolute value of u plus c. And then finally plug in what the u is, we get natural log of the absolute value of sine of x plus c. Right? That's the integral of cotangent. And again, I wouldn't necessarily memorize that, just remember how to do it, right? There's nothing too crazy hard about doing that. Okay, similarly for tangent, you could write tangent as sine over cosine. Now here, if you did the u substitution, the u would be cosine, the du would be minus sine. So you're going to end up getting a minus in your answer here. So that's why it's negative natural log of the absolute value of cosine is the answer. And by the way, that negative can come up here by the power property of exponents. And it turns out this would be the same thing as natural log of the absolute value of secant of x. Okay, remember 1 over cosine ends up being secant. Okay, now how would we integrate tangent squared? Now again, tangent squared is not in the right-hand side of anything over here, right? The derivative of tangent is secant squared, the derivative of secant is secant times tangent, but I don't see a tangent squared anywhere over here. So how would we do the integral of tangent squared? Well, let's remember here that there's actually a trig identity for tangent squared. So let's recall kind of the most famous trig identity is that sine squared plus cosine squared is 1. Okay, sine squared x plus cosine squared x is 1. Now, if we divide both sides of this equation by cosine squared, okay, we get this. Now, notice the left-hand side would be sine squared over cosine squared plus cosine squared over cosine squared. Well, of course, cosine squared over itself is 1, but what's sine squared over cosine squared? Well, that's the same thing as sine over cosine, that quantity squared. In other words, it's really tangent squared. Okay, so sine squared over cosine squared is tangent squared. Now 1 over cosine squared is the same thing as 1 over cosine times 1 over cosine, but 1 over cosine is just secant. So it turns out that just like 1 over cosine is secant squared, 1 over cosine squared is secant squared. So we have this trig identity. And again, I can never remember this identity. I can never remember if it's tangent squared plus 1 that's secant squared, or if it's secant squared plus 1 that's tangent squared. I can never remember it. So I always just kind of remember it based on starting with this original formula, dividing both sides by cosine squared. So notice tangent squared plus 1 is secant squared. Or another way of saying this is that tangent squared is secant squared minus 1. So notice that's what we're using here. Tangent squared is secant squared minus 1. Okay, now what's the integral of secant squared minus 1? Well, the integral of 1 is just x, of course. The integral of secant squared is tangent, right? Remember, the derivative of tangent is secant squared. So this is just tangent of x minus x plus c. Okay, so that's how we find the integral of tangent squared, is we write it as secant squared minus 1, and those are two things that we know how to do the integral of. By the way, we can get another third identity here by taking the original formula, original identity, sine squared plus cosine squared is 1, and in dividing by, instead of cosine squared, divide both sides by sine squared. Okay, if you divide both sides by sine squared, you end up getting this trig identity, right? Sine squared over sine squared is 1. Cosine squared over sine squared is cotangent squared. And 1 over sine squared is cosecant squared. Okay, so you kind of have these three trig identities. But I mainly just remember the first one, and I derive the other ones by dividing by either cosine squared or sine squared. Okay, now how can we find the integral of secant of x? Now, secant is 1 over cosine, and you might think, well, why don't we just do a u substitution? Write this as 1 over cosine, let u be cosine. Well, the problem is the du would be a minus sine x dx, but we don't have a minus sine x dx, right? So u substitution isn't going to work. Well, the secant of x, whoever came up with this, I think, had to be very clever. Okay, but the way you integrate secant is you do a clever way of writing 1. Okay, you do an interesting way of writing 1. We're going to multiply secant of x by 1, but the way of writing 1 is secant plus tangent over itself, right? Anything divided by itself is just 1. So do you agree, right, that the integral of secant would be the same thing as the integral of secant times 1, right? But this strange way of writing 1. Okay, now why did we do this? Well, if we multiply secant times this, remember secant is just secant over 1. Okay, anything is just that thing divided by 1. So if we multiply these two fractions, this fraction times this, we just need to multiply across the top, multiply across the bottom. Well, in the denominator, we just have secant plus tangent. In the numerator, we have secant times secant, which is secant squared, and then plus secant times tangent. Okay, well, this looks a lot messier than the original one. You might think, what was the point of doing all that? Well, it turns out that if you let u be the denominator down here, secant plus tangent, the du ends up being exactly the numerator. Okay, again, whoever came up with this was really clever, and there's no way of kind of knowing what to do. Oh, this is obvious that you have to do this. There's no way this is going to be obvious, but it just turns out that if you let u be the denominator, right, if u is secant x plus tangent of x, the derivative of u, the du, would be secant x tangent x plus secant squared dx, right? Derivative of tangent is secant squared. The derivative of secant is secant plus tangent. But notice that's exactly what we have here in the numerator. Okay, so this is really the integral of 1 over u du. Okay, and the integral of 1 over u du is natural log of the absolute value of u plus c. And then plug in what u was. It was secant x plus tangent of x. And by the way, that's a plus, not a times here. Okay, so again, this was not obvious. You almost just have to kind of memorize the technique for this one. But it turns out the integral of secant is natural log of the absolute value of secant plus tangent. Okay, plus c. Okay, now how could we find an integral like cosine squared? So by the way, not too many ones are like this, where you have to be super clever like this. I think you can do a similar thing with the integral of cosecant. Okay, you have to write cosecant times a clever way. I think it's like cosecant plus cotangent over itself. Okay, but most of these ones that we're going to look at are not ones you just have to kind of memorize the technique. Okay, so how could we find the integral of cosine squared? Okay, well, let's remember these trig identities. Now, one trig identity for cosine squared is that it's 1 minus sine squared, right? Because cosine squared plus sine squared is 1, so cosine squared would be 1 minus sine squared. But that's not the trig identity we're going to use. We actually have another trig identity for cosine squared, is that it's 1/2 times 1 plus cosine of 2x. Or in other words, it's 1 plus cosine of 2x, that whole thing divided by 2. Now, sine squared also has a similar one, and it's 1/2 times 1 minus cosine 2x. And by the way, that's not a mistake here. These are both cosines on the right-hand side here. Notice, by the way, what would happen if you added sine squared plus cosine squared? What if you added the right-hand side here plus the right-hand side there? What you would end up getting would be 1. Okay, try it. You'd have a 1/2 plus a 1/2, that's 1, but then you'd have a minus 1/2 cosine 2x and a plus 1/2 cosine 2x, that would add to 0. So the right-hand sides just add to 1 like you would expect it would. Okay, but it turns out, though, that instead of integrating cosine squared, if we integrated this thing that cosine squared is equal to, okay, it's easier to do. Okay, so the integral of cosine squared is the integral of 1/2 times 1 plus cosine 2x. Well, of course, you can pull the 1/2 out front. The integral of 1 is just x. The integral of cosine 2x, well, you could do a u substitution. By the way, if you were going to do a u substitution, you would want to split this up into two separate integrals. Do the integral of 1 dx plus the integral of cosine 2x dx, and then let the u be 2x. But I think we can do this in our head. Remember, the derivative of cosine 2x would be minus sine of 2x times 2. Okay, the integral of cosine 2x, though, is positive 1/2 sine 2x. Okay, and so that's our answer. Now you could distribute the 1/2 and get 1/2 x plus 1/4 sine 2x plus c, and that's the answer. Now, one other thing I want to point out is sometimes you'll see the integral of cosine squared written a different way, written in this way down here, and it turns out this answer is equivalent to this, and the reason is that sine 2x, there's a trig identity for sine 2x that says it's equal to 2 sine x cosine x. Okay, so if you write sine 2x as 2 sine x cosine x, then the 1/4 and the 2 become a 1/2, and so sometimes this is the way that you'll see the integral of cosine squared written like this. Okay, but either way is perfectly fine. By the way, you can do the same thing for integral of sine squared. Okay, this time you just have a minus here. It's 1/2 times 1 minus cosine 2x, so everything ends up being the same, only you have a minus there, and you have a minus there. Okay, so that's how you would integrate sine squared or cosine squared. Now, what about higher powers of sine or cosine? How could we integrate something like sine to the 4th or cosine to the 7th power? Okay, well, it turns out what we can do is use what are called these reduction formulas. Okay, now you don't need to memorize these, or at least I don't expect you to memorize these. These are kind of messy looking formulas. But where do these formulas come from, and how can we use them? Okay, so let's begin with how can we use the formulas, and then we'll talk about where do they come from. Okay, so let's use a reduction formula to evaluate the integral of cosine to the 5th power of x dx. Now you might think, why don't we just let u be cosine, and then we'd have like the integral of u to the 5th, right? But the problem is the du would be minus sine x dx, and we don't have a minus sine x dx. Okay, if this were cosine to the 5th of x times sine of x, then we would do that. Okay, but it's just the integral of cosine to the 5th. So what do? Well, notice we can use this reduction formula, and again, I'll explain where this comes from in just a minute, but where the n is 5. Okay, the integral of cosine to the 5th. So let's replace all these n's in this formula with 5. What do we get? Well, the integral of cosine to the 5th is going to be 1/5, right, 1 over n, times cosine to the 4th, right, because it's n minus 1, times sine of x, plus, well, it would be 4/5, right? 5 minus 1 over 5 would be 4/5, times the integral of cosine to the 3rd power, right? 5 minus 2. Now notice what happened is we reduced the power on cosine from 5 to 3. That's why it's called a reduction formula. We reduce the power on cosine. Now the question is, though, how do we integrate cosine cubed? Well, we can use the formula again. Okay, this time where we let n be 3. So if we use the formula again, okay, the integral of cosine cubed ends up being 1/3 cosine squared times sine, plus 2/3 times the integral of cosine to the 1. So we've reduced it from 5 to 3, and now we reduced it from 3 to 1. Well, we know how to integrate cosine to the 1, right? The integral of cosine is just sine, right? Positive sine. And if we do everything here, like distribute the 4/5, our final answer is this down here. Now, remember, 4/5 times 1/3 would be 4/15, but then we also have to distribute this 4/5 times 2/3, so it would be 8/15 there. And we have the integral of cosine is sine. So that's our final answer. So notice we had to use the reduction formula twice. Now, if this had been the integral of cosine to the 7th power, we'd have to use the reduction formula 3 times to get from 7 to 5, and then 5 to 3, and then 3 to 1. Okay, so the higher the power is, the more times you're going to have to do it. So it's a pain if you had a high power on x here, but it's at least a way that we could do this integral. Okay, so we didn't even theoretically have a nice way of doing this before. Now we do. Okay, same thing with the integral of sine to the 4th. Now notice with sine to the 4th, the reduction formula is very similar, although you have a minus here, and the cosines and the sines kind of flip spots here. Okay, but everything else is essentially the same. Okay, so the integral of sine to the 4th is minus 1/4 sine to the 3rd times cosine times 3/4 the integral of sine squared. Now here, how would we integrate sine squared? Well, we've already done that integral of sine squared before. Remember, we used the trig identity, but we could use the reduction formula again, and so that's what we'll do here. So we could do the integral of sine squared one of two ways. So remember back here, we did the integral of sine squared. We came up with this formula here. Okay, now by the way, if you do use the reduction formula, I think it ends up giving you this formula down here. But again, this is equivalent to this. If you just remember that sine of 2x is 2 sine x cosine x. Okay, but here I'll use the reduction formula. Integral of sine squared. Notice when you use the reduction formula, you get sine to the 0 power. It drops by 2. But sine to the 0, what's the integral of sine to the 0? Well, sine to the 0 is just 1. Okay, so the integral of 1 ends up just giving you x. Okay, so if you do everything correctly here, distribute the 3/4. By the way, when you do this integral, you want to make sure you put that whole thing in parentheses. So the 3/4 doesn't just go to this part here. The 3/4 also applies to this over here. That's why we have a 3/8 right here. 3/4 times 1/2. Okay, now where do the reduction formulas come from? Now, I'm not going to ask you to sort of rederive this formula, but I hate to just throw you a formula and just make it seem like it just kind of drops out of the sky. Well, the reduction formulas come from integration by parts. Okay, so how can we do integration by parts with this one? Well, we can write cosine to the n as cosine to the n minus 1 times cosine. Kind of like x to the 5th power is the same thing as x to the 4th times x. Okay, so cosine to the n is the same thing as cosine to the n minus 1 times cosine, right? Like cosine to the 5th would be the same thing as cosine to the 4th times cosine. Okay, now that we've broken it apart like this, we can let the u be cosine to the n minus 1 and the dv be cosine x dx. Right, so I've written the dv down here, cosine x dx. The u is cosine to the n minus 1. Now that's the way I've written it here. This is just a difference in notation, but these things mean the same thing. This is cosine of x, that whole thing to the n minus 1. Okay, well, if dv is cosine, what's v? Well, v would be the integral of cosine, which is positive sine. Okay, remember the derivative of cosine would be minus sine. The integral is positive sine. What's the derivative of cosine to the n minus 1? Well, we can use the chain rule, right? So if u is cosine to the n minus 1, du would be, well, we bring the n minus 1 out front, so we have n minus 1 times cosine to the n minus 2, right? We lower that by 1. Okay, but then times the derivative of that inside function, the derivative of cosine, which is minus sine. Okay, minus sine x and dx. Okay, now we can rewrite this. I bring this minus out front, so we get minus n minus 1 times cosine to the n minus 2 of x, because that's what this is, times sine of x dx. Okay, now if we use integration by parts, this is what we get. So this thing should equal uv, so I've written the u, okay, cosine to the n minus 1, v, which is sine, minus the integral of v, which is sine, du, which is all of this. Okay, and that's what I've written right over here. Okay, it's kind of a mess here. But then notice what we can do is take this negative here. So this is sine times negative of this whole thing. And it's not sine minus this thing. It's sine times the negative of this. So be careful of that. This negative can come out front. It's a plus. And also the n minus 1 can come out in front of the integral because it's a constant, okay, with respect to the variable that we're integrating with, right? So it doesn't have an x in it, so we can bring the n minus 1 out front. So what we're left with on the inside here in the integrand would be cosine to the n minus 2, but then times sine squared. Okay, well, sine squared is the same thing as 1 minus cosine squared. Okay, so we can write it like this. And finally, we can rewrite this as cosine to the n minus 1 times 1 is just, or I'm sorry, cosine to the n minus 2 times 1 is just cosine to the n minus 2. Minus, well, what's cosine to the n minus 2 times cosine squared? Well, that would just be cosine to the n. So in other words, we can distribute this cosine to the n minus 2, do it this times 1 minus this times cosine squared. And then we can split that apart into two integrals. Okay, and we still have the n minus 1 out in front of both integrals. So we have cosine to the n minus 2 times 1, that's here. Cosine to the n minus 2 times cosine squared, that'd be just cosine to the n. We have that here. Okay, so notice what we have is this integral is equal to this plus this minus this. Well, notice you might think, aren't we just spinning our wheels here? Because notice I have a cosine to the n over here. That was my original integral. Right, so it seems like, oh man, I didn't make any progress at all. I did all that hard work and I have the same integral here. Well, it turns out what you can do is add this term, this integral, n minus 1 times this integral, to both sides of this equation. So we let cosine to the n equal this plus this plus this. Add this to both sides, so we have n minus 1 of these integrals plus 1 of those integrals. So what's n minus 1 of them plus 1 of them? It would just be n of them. So if we add this term to both sides, we get n times that cosine to the n equals this plus this. Okay, we have rewritten those terms there. So finally, divide both sides by n, and you get cosine to the n equals this plus this all over n. Or another way of writing it is that this term over n, which is like 1 over n times that, and this thing over n is just like n minus 1 over n times this integral, and that's the reduction formula. Okay, so I realized that was messy. Okay, that was a messy computation. I'm not going to ask you to rederive it, but really where it comes from is integration by parts. Okay, but you have to do this clever trick of adding an integral to both sides. Okay, actually adding n minus 1 of those integrals. And by the way, you can do the exact same thing for sine of n. Okay, the integral of sine of n. Okay, that reduction formula can be obtained in a similar way. Okay, now how would we integrate something like this? So we're not going to use the reduction formulas anymore. If this were just integral of sine to the fourth, we'd do a reduction formula, but this one's much easier. We have sine to the fourth times cosine. This is much easier. We can just let u be sine, and the du will be the cosine x dx. Okay, so what we have is the integral of u to the fourth du. Right? You might wonder, where'd the cosine go? Well, the cosine x dx, that whole thing became the du. And the sine to the fourth is really just u to the fourth. Okay, the integral of u to the fourth du is u to the fifth over 5. So we just have sine of x to the fifth over 5 plus c. Or another way of writing that is 1/5 sine to the fifth of x plus c. Okay, so that was much easier, I think, than using the reduction formulas. It really helped to have that cosine out front. Okay, now what about if we have something like this? Instead of having just a cosine here, we have sine to some power times cosine cubed. Okay, this time if we let u be sine, the du would be cosine of x dx, but we have a cosine cubed here. So how do we deal with that? Well, we're eventually going to do a u substitution, but forget this part here right away. What we do, if we have a sine to some power times cosine to some power, it's good if at least one of these powers is odd. And I'll show you why in a second here, but we have a cosine cubed. So what we're going to do is break off one of those cosines and write cosine cubed as cosine squared times cosine. Now, eventually, we're going to do a u substitution where we let u be sine, and the du will be this part out here, cosine x dx. Okay, but then what about this cosine squared? How do we deal with that? Well, cosine squared is 1 minus sine squared. Okay, so what we have is sine to the 10th times 1 minus sine squared times cosine x dx. Now we can do our u substitution, let u be sine. So what we have here is u to the 10th times 1 minus u squared, and then this out here is the du. Okay, now this is much easier to integrate. How do we integrate u to the 10th times 1 minus u squared? Well, distribute the u to the 10th. Just write this as u to the 10th minus u to the 12th. And then that's easy to integrate, right? It's just u to the 11th over 11 minus u to the 13th over 13. Finally, plug in what the u is, right? We get 1/11th sine to the 11th of x minus 1/13th sine to the 13th of x plus. Okay, now what about something like this? We have the integral of sine to the 5th times cosine to the 8th. Now, it turns out it's not going to work too well to break off a cosine here. I'll say why in a second. Really, the reason is because you have an even power on cosine. Okay, but we have an odd power on sine, which is good. So what we can do is break off the sine. Okay, so we have a sine to the 5th. We can write it as sine to the 4th times sine. Okay, and eventually we're going to do a u substitution and letting u be cosine, and the du will be sine, actually minus sine. Okay, but so how do we do this? Well, we've broken off we have sine to the 5th, so we've written as sine to the 4th times sine. We can write sine to the 4th as sine squared squared. Okay, and sine squared is 1 minus cosine squared. So notice we have everything now in terms of cosine, with the exception of this sine here. So we're going to do a u substitution where u is cosine, the du will be sine, or minus sine x dx. Okay, now notice the reason this worked out well was because I could write sine to the 4th as sine squared squared. If this had been sine to the 6th, I could write this as sine squared cubed. Okay, if this had been sine to the 10th power, let's say, I could write it as sine squared to the 5th. Okay, but if it were sine to some odd power, though, it would be sine squared, and you'd have to have a fraction out here, which would end up being a problem. Okay, so it works out well if you have an odd power on sine or cosine, because once you have an odd power, if you break off the sine, you end up with an even power, which means we can write it as sine squared to the some whole number, some integer here. Okay, so suppose we've done this. Let's do our u substitution. U is cosine, du is minus sine x dx. And we get 1 minus u squared times u to the 8th du. But notice we have a negative out front because the du ended up being a negative sign. So we need to put in a negative there and put a negative out front. Okay, so how would we integrate 1 minus u squared times u to the 8th. Well, this is really just a polynomial if you multiply everything out. Now remember, 1 minus u squared squared is like 1 minus u squared times itself. And if you FOIL this out, you get 1 times 1 is 1. You get a minus u squared and another minus u squared. That's minus 2u squared. And finally, minus u squared times minus u squared is plus u to the 4th. So we can rewrite this as this. Okay, and then we multiply by u to the 8th. So we distribute the u to the 8th. We get u to the 8th minus 2u to the 10th plus u to the 12th. Okay, and we still have this negative out front. And now we know how to integrate that, right? The integral of this du is going to be u to the 9th over 9 minus 2u to the 11th over 11 plus u to the 13th over 13. We can distribute the negative here and make sure you put this in parentheses so the negative doesn't just apply to this. Negative applies to the whole thing. So this negative there becomes a plus, and this plus becomes a minus. And finally, plug in back what the u is, right? The u is cosine, and so this is our final answer. So again, this worked out well because we had an odd power on sine. If we had had an even power on both of these, it would be much trickier, because if we tried to break off a sine, like if this had said sine to the 6th power instead of sine to the 5th, if we tried to break off a sine, we'd have a sine to the 5th here. We'd have to write this as sine squared to the 5/2 power. So that'd be 1 minus cosine squared to the 5/2. So it'd be 1 minus u squared to the 5/2. But 1 minus u squared to the 5/2, we can't just FOIL things out. If you have 1 minus u squared to a nice whole number power, you can just multiply it by itself several times. But if it's to a fractional power, you would get stuck. Okay, so notice, here's a procedure that we can use to integrate sine to the m times cosine to the n dx. Okay, if the n is odd, essentially, so the power on cosine is odd, you split off a cosine. Okay, and then you do this relevant identity that cosine squared is 1 minus sine squared, and you let u be sine so that the du ends up being the cosine x dx. So that cosine x that you split off becomes part of the du. Okay, now if the power in m is odd, you could split off the sine. Okay, and then eventually let u be cosine. Okay, now if they're both odd, then you can really choose which one you want to split off. In that case, I would pick whichever one is smaller. If m is smaller or n is smaller, pick the smaller one to split off. So it's like, if it's like sine to the 13th times cosine to the 3rd, I would split off the cosine because it has a smaller power. Now, if they're both even, it turns out what you have to do is use these identities here, okay, to reduce the powers on sine and cosine. So if you like sine to the 10th times cosine to the 8th, but that's much harder, and I'm not going to ask you to do that. But it's, it's not like it's impossible or anything. It just takes a little bit of work, but I'm not going to ask you to do that. So it's nice if at least one of the powers m or n is odd. And by the way, you can do a similar thing for integrals like this, where you have tangent to some power times secant to some power. Okay, only in this case, it's nice if the n, the power in secant, is even. Okay, it's good that the m is odd again, but you actually want the power in n to be even. So if either n is even or m is odd, or both, you can use this procedure, which I'll do an example here in a second. The hard case would be if m is even and n is odd. Okay, but basically what you're going to use is these relevant identities. Remember, we had sine squared plus cosine squared is 1. Well, we also had these identities involving secant and tangent. Okay, only when we split off the secant here, the reason we want it to be an even power is because we're going to split off a secant squared. Because we'll eventually let u be tangent, then du will be secant squared x dx. Okay, that's why we want the power to be even, because we're going to split off a secant squared, and what remains will be an even power of secant, which is good. Now, in the other case, what we're going to split off is a secant times a tangent. Okay, and the reason that will be good is because we'll eventually let u be secant, and then du will be secant tangent. Okay, so let's do an example. Suppose we have tangent to the 12th times secant to the 6th. Now, if this were involving sines and cosines, this would be exactly the bad case, because you have an even and an even. But remember, we wanted the power in secant to be even. Okay, if at all possible. So notice what we do is we split off a secant squared. So we write secant to the 6th as secant to the 4th times secant squared. Because eventually we're going to let u be tangent, and the du will be secant squared x dx. Okay, now secant to the 4th is the same thing as secant squared, and secant squared, if you remember, there's an identity for secant squared, it's tangent squared plus 1. Okay, so notice that what we have is everything in terms of tangent, and then times a secant squared x dx. So what we can do is let u be tangent. Okay, and then du is secant squared x dx. So what we have is integral of u to the 12th times u squared plus 1 squared, okay, du. Okay, so how do we integrate u to the 12th times u squared plus 1 squared? Okay, well, u squared plus 1 squared is like u squared plus 1 times itself. And if you FOIL that out, you get u squared times u squared is u to the 4th. U squared times 1 plus u squared times 1, that'll give you 2u squared. And finally, 1 times 1 is 1. Okay, so that ends up being u to the 4th plus 2u squared plus 1. That's this. Okay, and then we still have times u to the 12th. So if you distribute that u to the 12th, you get this. And this is easy to integrate. The integral of u to the 16th is u to the 17th over 17. Then we get 2u to the 15th over 15 plus u to the 13th over 13 plus c. And finally, plug in what the u is, right? The u is tangent. And so this is our final answer. Okay, so again, notice what we did was we broke off a secant squared. Okay, and one other example like this. Notice we have tangent cubed times secant to the 8th. Well, the secant is even, which is good, but the tangent power is also odd. So we kind of have a choice. Do we want to break off a secant squared, or the fact that tangent is odd, what we could do is break off a secant times tangent. And I think the tangent power is, since the tangent power is lower, I think it's going to be easier to break off a secant tangent. Because eventually we're going to let u be secant and the du will be secant tangent. So if we break off a secant tangent, what we have is tangent squared times secant to the 7th times secant times tangent dx. Okay, so we've broken off both a tangent and a secant. Because eventually what we're going to do is let u be secant, and then du will be secant times tangent. So we want all this to be in terms of secant. Well, how do we do this? Well, tangent squared is secant squared minus 1. Again, using that identity here. So we have the integral of secant squared minus 1 times secant to the 7th times secant times tangent dx. Okay, well now do the u substitution. Okay, where the u is secant, so the du is secant times tangent dx. So what we have is the integral of u squared minus 1 times u to the 7th du. Okay, now distribute the u to the 7th. Fortunately, we don't have any power on here, so we don't have to FOIL anything out. Just distribute the u to the 7th. Well, that'd be u to the 9th minus u to the 7th. And the integral of that du is going to be u to the 10th over 10 minus u to the 8th over 8. And finally, plug in what the u is. Okay, the u is secant of x. Okay, so we get 1/10 secant to the 10th of x minus 1/8 secant to the 8th plus c. Okay, now how could we integrate something like this? Okay, cosine of 5x times sine of 3x dx. Now you might think, why don't we just let u be cosine of 5x, and then wouldn't the du be this? Well, if the u is cosine of 5x, the du would be minus sine of 5x times 5. Now the minus is not a problem, the 5 is not a problem, but the sine of 5x, we have a sine of 3x, not a sine of 5x. Or same thing if we let u be sine of 3x, wouldn't du be cosine of 3x times 3? But we don't have a cosine of 3x, we have a cosine of 5x. So how do we integrate this? Okay, well, it turns out that we can integrate things like this, like sine of mx times cosine of nx, or sine of mx times sine of nx, or cosine of mx times cosine of nx. We can integrate this using these trig identities. Now, where do these identities come from? I'll explain that in a second here. We're almost done with the video. But then also, how do we use these identities? Okay, so this is an identity for sine alpha cosine beta, or sine alpha sine beta, or cosine alpha cosine beta. We have these identities. So where do these identities come from? I'll explain that in a minute. But also, how can we use them? Okay, so I've rewritten the identities right here that we're going to use. How would we integrate sine of 5x times cosine 3x dx? Well, notice which of these identities are we going to use? We're going to use the top one because this has a sine times a cosine. Now the alpha is 5x. By the way, the alpha is not just 5, it's 5x. The beta is 3x. Okay, so sine of 5x times cosine 3x ends up equaling 1/2 sine of 5x minus 3x, which is 2x, plus sine of 5x plus 3x, which is 8x. Okay, so sine 5x times cosine 3x is actually 1/2 times sine of 2x plus sine of 8x. And the reason it was 2x was that's the same as 5x minus 3x. And the reason it's 8x is that's 5x plus 3x. Okay, well now this is something we know how to do, right? We can take the 1/2 out front. Now how do we integrate sine of 2x plus sine of 8x dx? Well, we could do this in our head like we're going to do it here. Or if you wanted to do a u substitution, what would you do? Would you let u be 2x or u be 8x? Well, you just split this up into two different integrals. You write this as sine of 2x, so you'd have 1/2 sine of 2x plus 1/2 sine of the integral, or 1/2 the integral of sine 2x dx plus 1/2 the integral of sine x 8x dx. Okay, so you split it up into integral of this plus the integral of this. The first integral, you let the u be 2x. The second integral, you'd let the u be 8x. But I think we can do this in our head. Right? Remember, the derivative of sine of 2x would be cosine of 2x times 2. The integral of sine 2x ends up being negative 1/2 cosine 2x. Okay, the integral of sine of 8x is going to be negative 1/8 cosine of 8x. Okay, now we can distribute the 1/2. We get negative 1/4 cosine 2x minus 1/16 cosine of 8x. Okay, plus c. Don't forget the plus c. Okay, so that's how we use those identities. So let's actually do one more. Okay, what would be the integral of cosine of 4x times cosine of x? Okay, well, notice this is the identity we're going to use. Okay, cosine of alpha times cosine of beta, because we have a cosine times cosine. In this case, the alpha is, 4x, and the beta is just x. Okay, so notice what it ends up being is 1/2 cosine of alpha minus beta plus cosine of alpha plus beta. Okay, so what we get is 1/2, and I just pulled the 1/2 out in front of the integral right at the beginning here. Integral, cosine 4x times cosine x is going to be 1/2 times the quantity cosine of 3x, right, which that's 4x minus x, plus cosine of 5x. That's 4x plus x. Okay, now the integral of cosine 3x ends up being positive 1/3 sine 3x. Integral of cosine 5x ends up being positive 1/5 sine of 5x. Okay, and we still have the 1/2 to distribute, so we get 1/6 sine of 3x plus 1/10 sine of 5x plus c. Okay, now where does this come from? So this is our last sheet. Where do these identities come from? So these are probably not familiar. I don't always have these things memorized. So where do they come from? Now I'm going to use A and B instead of alpha and beta. But where do these identities come from? Well, a couple identities that may be a little more familiar to you would be these. So maybe they are, maybe they're not. The sine of A plus B is the same thing as sine A cosine B plus sine B cosine A. Okay, there's also one for cosine of A plus B that says it's cosine A cosine B minus sine A sine B. So this may be familiar to you. By the way, if you let the B be A, so you'd have sine of A plus A, that'd really be sine of 2A. Notice it's the same thing as sine A cosine A plus sine A cosine A. That'd be 2 sine A cosine A, right? So sine of 2A would be 2 sine A cosine A. That's an identity. So, okay, so you can derive that one, though, from this one. Okay, so it turns out what we can do is remember a couple things here. What's sine of A minus B? Well, if we have an identity for sine of A plus B, we can take the b's in this identity and replace them with minus b's. Okay, so A minus b is the same thing as A plus a negative b. So we replace all the b's in this formula with negative b. So sine of A minus b would be sine of A cosine of minus b plus sine of minus b times cosine of A. Now remember a couple things about sine and cosine. Cosine is what's called an even function. Cosine of negative x equals cosine of x for every value of x. By the way, you can see that based on the graph of x. The graph of cosine of x, it's symmetric with respect to the y-axis. Right? So cosine is what's called an even function. A function's even if f of negative x equals f of x. Okay, for example, the absolute value of x is an even function. Notice its graph, that little v, is symmetric with respect to the y-axis, right? The y-axis is kind of like a mirror for the left side and the right side. Same thing with x squared. Okay, x squared has the property, if f of x is x squared, it has the property that f of negative x equals f of x. And again, x squared is symmetric with respect to the y-axis. Okay, so cosine's an even function. So notice cosine negative b is the same thing as cosine b. Now sine is what's called an odd function. Sine of negative x is equal to negative sine of x. Okay, so a function is odd, function f is odd if f of negative x equals negative f of x. Okay, so for example, an odd function would be like x cubed. Okay, is an odd function. It has this property. And odd functions are symmetric with respect to the origin. Okay, so, but the point is sine of negative b is negative sine of b. Okay, so we can rewrite this like this. So now notice we have these two identities. one for sine of a plus b and one for sine of a minus b. Sine of a minus b ends up being this. Well, what if we add sine of a plus b plus sine of a minus b? It should end up being this thing plus this thing, right? Sine of a plus b plus sine of a minus b should equal this plus this. Well, notice when we do this plus this, we have a sine b cosine a and also a minus sine b cosine a. So those things will add to 0. They'll go away. Here we have a sine a cosine b plus a sine a cosine b. That gives us 2 sine a cosine b. So notice if we have sine of a plus b plus sine of a minus b, what we end up getting is 2 sine of a cosine of b. Okay, and if we divide both sides by 2, now we have sine a cosine b equals this thing over 2, or 1/2 of this thing, and that is our identity. Sine of a cosine b is 1/2 of this. That was one of our identities, right? That was this top. Let's see. Yeah, it was this top one here. Okay. Sine a cosine b equals this. Okay, that was the one that we came up with. By the way, you can come up with the other two formulas, these ones here, by doing say cosine of a minus b. So we have a cosine of a plus b. If you do cosine of a minus b and write out what it is, and then you can come up with these other two identities. If you do cosine of a minus b plus cosine of a plus b, or cosine of a minus b minus cosine of a plus b, you can derive these identities. But again, I'm not going to ask you to even memorize these. I'll give you these identities if you need them on a test or an exam, but that's where these come from. Okay, so this video has been about integrating trig functions. The next video will be about doing what are called trig substitutions. And those are going to be integrals where the original integral looks like it may have nothing to do with trigonometry, but we're actually going to use trig functions to help us solve those integrals.